What if I told you there's one single mathematical idea that connects the crazy up and down path of a stock chart with, say, the flight of a bee? It's this amazing concept that actually finds a deep, surprising order hidden inside what looks like just pure random chance.
So, really, what is the link between a gambler going broke at a casino and an animal that's just out looking for food? I mean, they seem like they're from completely different worlds, right? But believe it or not, they're both playing by the exact same mathematical playbook. Well, the answer is the random walk. And look, this is one of the most fundamental ideas in all of science. So today we're going to break down what it is exactly and why it is just so powerful. All right, so to really get our heads around this, let's start with a classic and pretty memorable analogy. It's called the drunkard's walk. Yeah, it's a little wobbly, but it is the perfect way to understand the main idea here. So, at its core, a random walk is, well, it's just that simple. Just picture a path with no memory, absolutely no plan. Every single step is totally independent of the one before it. It's like a pure roll of the dice every single time. Okay, so the official definition is basically a mathematical process that describes a path made up of a series of random steps. The term itself was actually coined way back in 1905 by a mathematician named Carl Pearson, and honestly, it's been helping us make sense of the world ever since. All right, let's build one of these things from scratch. Seriously, the best way to get it is to look at the simplest possible version, just a straight line, where you can only go in two directions. So here's how it works, step by step. You start at the number 0. Then you flip a fair coin. If it's heads, you take one step to the right, to +1. If it's tails, you take one step to the left, to -1. And then you just repeat. That's it. The path you end up tracing, that is a perfect one-dimensional random walk. And check out what starts to happen as you take more and more steps. Right, after one flip, you can only be at -1 or +1, simple enough. But after just 4 flips, look at all the possibilities. You could be at -4, -2, 0, 2, or 4. The walker's potential stomping grounds just start to spread out, exploring more and more of that number line. Okay, but get ready for this, because this is a truly mind-bending fact. Even after, say, 1,000,000 steps, if you could somehow average out every single possible path the walker could have taken, their expected position is always 0, right back where they started. Isn't that wild? So wait a second. The average spot is always 0, but that does not mean the walker just stays put. Oh no, in fact, they wander away. And the typical distance they get from the starting point grows, but it follows this very specific rule. It's the square root of the number of steps. So think about that. To get twice as far away, you don't just take twice as many steps. You have to take 4 times as many. It gets harder and harder to push into new territory. And this all leads to a pretty famous and honestly kind of sobering result called recurrence. Here's the deal. In one dimension, a random walker is guaranteed to eventually come back to its starting point. This is the cold, hard logic behind the gambler's ruin. See, a gambler with a finite amount of money is on a random walk. The house, on the other hand, has basically infinite money. Since the walk is guaranteed to eventually hit every point again, it's also guaranteed to eventually hit 0. And when it does, the gambler is wiped out. Okay, so we know a one-dimensional walker always comes back home. But what happens if we give them a little more room to roam? What about 2 dimensions, like walking around on a city grid? Or even 3 dimensions, just floating in open space? And this is where we get to one of the absolute weirdest results in all of mathematics. Just look at this. In 1 dimension, that line we talked about, and even in 2 dimensions, like a flat plane, the walker is pretty much guaranteed to find its way back home. It's almost a certainty. But add just one more dimension, go into 3D space, and suddenly the probability of ever returning to the start just plummets. It drops to only about 34%. That extra dimension just opens up an infinity of new ways to get lost forever. This whole idea is captured perfectly in this famous saying. A drunk man will find his way home, but a drunk bird may get lost forever. See? The drunk man, he's stuck on a 2D surface, the ground, so he's guaranteed to eventually stumble his way home. But the drunk bird, it's flying around in 3D space, and it really truly might get lost forever. Okay, so up until now, we've been talking about these separate individual steps, right? One step, then another. But in the real world, a lot of motion looks continuous. It looks smooth. So how do we bridge that gap?
What's the connection between our little step-by-step model and the smooth flow of things in nature?
Let's just ask a what-if question. What if our walkers started taking incredibly tiny steps, but took them incredibly fast? What would that kind of motion even look like?
Well, when you do that, when you shrink the steps and speed them up, the walk actually smooths out. It becomes something mathematicians call a Wiener process. Now, that's just a fancy name for the kind of motion you see in diffusion, or in something called Brownian motion. You've seen this. It's that random, jiggling dance of dust particles in a sunbeam, or the way a drop of ink just spreads out in a glass of water. At the tiniest, microscopic level, it's all just countless little random walks happening at once.
And this, right here, is where it all clicks into place. Because this isn't just some abstract math game. The random walk is a fundamental pattern that nature uses again and again and again. Let's just run through a few places you'll find it.
So, first up, in finance, there's something called the random walk hypothesis. And it basically says that changes in stock prices are random and unpredictable, just like the steps of our walker. The idea is that past performance gives you no real clue about what's going to happen next.
Then there's computer science, where algorithms use random walks all the time. I mean, to estimate the size of the entire World Wide Web, a program can basically go on a random walk, jumping from link to link. They're used in image editing to figure out what's the foreground and what's the background. They even power recommendation engines, like when Twitter suggests who to follow. That's a random walk through the network of all of us.
And in biology, wow, the applications here are just stunning. The path an animal takes when it's looking for food, that can be modeled as a random walk. The way genes randomly drift through a population over many generations, that's a random walk too. Even the cascade of neurons firing in your own brain, or the movement of molecules in the very air you're breathing, it all follows this fundamental pattern. It's like a hidden code for the natural world. Okay, so let's zoom out and pull all of this together. We've seen how something as simple as flipping a coin can lead to these incredibly complex and widespread phenomena. So what's the big takeaway? What's the point of all this? Well, here it is. This is the most profound insight you can get from the random walk. While any single individual step is completely unpredictable, it's just a whim of chance, the collective behavior of millions and millions of those steps, that creates large-scale patterns that are surprisingly predictable. We can't predict the next step, but we can predict the general shape of the entire journey. Randomness, it turns out, has its own kind of hidden structure. And that leaves us with one final pretty tantalizing thought. If a process as simple as flipping a coin can generate such rich, structured, and predictable patterns, what does that suggest about all the other complex systems we see all around us? From the way galaxies form to the evolution of life itself. How much of the beautiful complexity that surrounds us might just be the elegant and maybe even ineditable result of simple, random chance doing its thing?